Hello, my name is Safran. I'm going to talk about the Handguiding industrial robots. First, I will do a little introduction of what the technology is. Then I will talk about the required hardware to develop this technology, also the software. And then we will go through all the stages that we need to cover to deploy this technology, and then some development on the current applications on our application, and finally some videos. So here, the hand guiding technology is an interface that we provide the user that can grasp this joystick and move the robot with their hands. So the robot will read the force applied by the user and move towards this direction. So it is an intuitive way of working with the robots for maybe the people that is not quite familiar with that. So we have covered already the certifications, but we manage the collaborative robots one because it is a collaborative robot application, and despite it is done in an industrial robot. And then the second one is on the human physical performance, because we are avoiding the user to move loads or easing the process of programming, so it will increase its performance also. And then the required hardware that we need is an industrial robot, and this robot has more advantage than using the collaborative ones. They can manage higher payloads. For example, the one that we have downstairs is around 200 kilograms. So we can manage different elements. And then the second element is the force and torque sensor that we will use to measure the effort that the user is applying on the robot, so we can compute the desired movement. And the last one is a joystick that it has 3 buttons. One will act as a deadman switch that, as Isidro explained, if we release it or we totally press it, the robot will stop. And the 2 upper buttons, we can program them as the application needs. So here in the software, you can see a diagram between the communication of the hardware with the software. And the main module is the Handguiding module that reads the effort on the sensor and also the robot position. So it will compute the command to apply to the robot. And to connect the hardware to the software, we use the framework ROS also. And for communicating the FT sensor, we are using CAN communication or Ethernet communication that will provide us the effort that is applied on the sensor. Then for the joystick, we are connecting the joystick directly to the robot, and we are reading the signal of the joystick through a driver in the robot and connected to the ROS. And for the robotic arm, we are using the UDP communication that it can work in high frequencies at 250 Hz. So here in the case of ABB, it is the external weight motion library, and in the KUKA, the robot sensor interface. Now, to deploy this technology, we will cover 4 stages. The first one is the dynamic HTML parameters. And for those who are not familiar with that, it is a way that we use to represent the robot description. And we are only basing on the length here of the links. So we have some restrictions on the orientation positioning, and we will get the transfer between one joint and the next one. So with 4 parameters for each pair of joints, we can extract the whole configuration of the robot. So it is a reduced way to represent it. and we can get the direct and the inverse kinematics. The next step is to tell the system where the sensor is placed and also where are we going to apply the force. This step is quite important because if we configure badly the application point, it can happen that you push the robot and the robot goes to you. So we have to calibrate it okay. And then when we have all the geometrical aspects calibrated, we have to calibrate the sensor. This process is also crucial to know the constant effort that is being applied on the sensor. For example, what we do is we eliminate the constant effort and we only keep the effort applied by the user. So this process consists of aligning each sensor axis in every direction. So we store 6 positions that the robot will perform automatically and do by itself the calibration. And the last step is adjusting the controller response. Once we have the calibration, we can test the move of the robot, and it can be that it is quite hard to move it or quite soft. So we have these 3 parameters that we can modify to obtain a smooth response. Here you see the weight of the reinforcement values. It can happen that if we apply a torque, the robot will not see that effort, so we can put the value, for example. Then the next one is the system inertia, that it affects to the start and the finish of the robot movement. If this value is too high, it can happen that when we release the force applied on the robot will continue moving. So we should reduce this. And the next parameter is the system frictions, that it applies some resistance during the movement. Here again, if the value is quite high, it will be so difficult to move the robot. So the aim of this stage is to find a balance between all the parameters to have the response that we want. So here, these are current solutions in the market that are all collaborative solutions. And we can see in the panel example that the operator is moving the robot with 200 devices. And here in the universal robot, we also see that the operator is moving the robot by their hands and programming some positions. Here, the advantage of using collaborative robots is that the robots are so light that we can move with our hands. And then a disadvantage of that is that the payload that they can manage is quite low. For example, in universal robot, I think they can move up to 20 kilograms, so it is not working in naval industry, for example. And here, our solution is based on industrial robots that we can move the payload that the robot can. So we have the first approach in the ABB robot, that is velocity commanded, and the output that we get from the controller will directly send to the robot. But in the KUKA and the COM-out solution that we have to command in position that will require additional computing. And for obtaining the smooth response that we get with the ABB, we are computing the command in a higher time that we are commanding. So we are converting each time the target. And here in the applications, when we place it, like you can see in this image, like the sensor attached directly to the robot TCP. With that, we only can move known loads. And to do that, we should calibrate the sensor also with the load attached. So because all that you put down the sensor will affect the measurement. So to have a more adaptable solution, we are putting the sensor outside the robot TCP. So if you attach something down the sensor, it doesn't affect. So this solution is the one that we have implemented downstairs. And the next application that we have is the trajectory programming. And for doing that, we have programmed the buttons to store the position when we press some button and modifying the accuracy. The accuracy modification is mainly the variation of the speed of the robot. It would move faster or slower, so we can handle this better. And the Deadman switch is also implemented here. So we need the Handguiding module and an additional module to store the trajectory and send it to the robot. Okay, and we have the graphical user interface to the process to the operator. And so briefly, we are here storing the global points that we want to program. We can enable and disable the controller. And the next lines are visualizations to let the user know what is the status of the controller. And the last button of execution of the trajectory, when we got the set points are the same as the stored ones, we can send all the trajectory to the robot. And here we can see the example on the KUKA robots. That the operator is moving the robot TCP and interacting with the buttons to program the trajectory. So then the robot will perform the trajectory automatically. And here we can see that the movement is quite soft instead of being commanded in position. And now here the robot performs the trajectory. And this is for welding a pipe. And here is the same, but in APP robot. We also see that our colleague is moving the joystick and programming a trajectory. And then the robot will go and execute the welding of this only. So here we can see also that it's a soft movement. So we got a smooth response with position control and velocity control. Okay. I don't know if you have any questions on this first application.
What sensor was installed directly at TCP?
Yeah, putting it outside the TCP.
Okay. Are there any applications where you put it directly to the TCP and apply loads with the sensor, or is the sensor always there?
You put it directly on the TCP. For example, if you are grasping some element, you can see you have grasped it or maybe the load is falling because you will see a change. But we think that the best for moving loads is to put it that outside. And now we are going to move into a collaborative application. Here, the PlasmaCAD application. The same contents, the introduction. Here are some safety aspects. Then the application, the graphical user interface, and finally some video demonstration. So here you see an overview of the fields that we can use collaborative robots. So in the field of manufacturing, it's basically pick and place, welding, some assembly. And in the field of agriculture, again, the pick and place, in harvesting, and also in harvesting, what they are using is mobile platforms together with the collaborative robot. Also in agriculture, they can use order preparations and quality in general for all the industries. And in the maintenance field, we have the teleoperations and fastening and fastening elements and some pitching. So our application will be in the welding aspect. So here, the plasma cut application is a process to deploy a robot in a scenario, and the robot will be able to localize and extract the cutting plane and perform the cut. So this is based on artificial vision, and with that, we get a portable solution that, because as you will see later, the robot is attached to a magnetic base. It is also easy to deploy for the users with different parameters. And the main advantage is that the robot can be placed at hazardous environments and also difficult access areas, because in the naval industry, maybe there are small scenarios or like that. And then we can adapt the application by changing the tool or changing the geometry in order to cut. In the safety aspects, these are related to the cutting process, and that will be noise, electrocution because of the electrical devices, and projection sparks with the associated risk of the fire and heat. So to protect this, we will wear some boots and earring protections, masks, and glasses when we are cutting. And here, our application in the hardware side, we have these elements. The first one is the camera support and the lens protection to protect the glass of the camera during the cut. Then we have a UR10 robot that weighs around 30 kilograms. Then the mag switch cobot that it also weighs 30 kilograms. What we do is to attach the robot to the magnet, and then the magnet we can place it into the ceiling or to the wall, so we can move from one place to other of the environment. Then we have the 3D camera, the IntelliReal Sense, that has a range between 11 centimeters to 10 meters, so we can see close views and also far views. And the plasma cut machine that we are using is the Hypertherm, that it also requires some air supply to clean the cutting during the process. So in the software side, we are using Ubuntu 18 with Rust Melodic. All the development is done in Rust. And the library that we are using to extract the planes and do all the computing is the Point Cloud library, that it has algorithms for filtering, reconstructing, and it is an open source library also. And then to extract data from the camera and to extract data from the robot and also send commands to it, we need some drivers. And we also need the cut of the environment and cutting parameters. And then in the module side, we have the calibration of the camera, the module for localization of the robot inside the cut, and then extracting the plane with the trajectory points and sending to the robot. So here, when we deploy the technology, we have two sequences, the offline sequence and the online sequence. The offline sequence covers all the part of the calibrations of the camera, here with a chessboard pattern, as Claudia explained before. And then we have to calibrate the tool. That for doing that, we follow the classical 4 points method with the calibration, that we set a fixed point in the space and we reach from 4 different orientations. Then we need to move all the hardware to the environment and connect everything. And we need to define the position of the cat that we can extract it directly from the file. So here, when we have all the calibrations on all the devices inside the area, we can start doing the online sequence. That the first step will be the reconstruction of the scenario. The robot will move to different positions, take some data, combine them, and then we can start localizing the robot. So for doing that, we see here that an interface of the cat will open, so we need to interact with it to tell the system more or less what is the position of the camera. So with that, we give the initial estimation to then apply the refinement process, that it is the algorithm iterative process points. And it is an algorithm that it minimizes the distance between a source cloud and the target cloud. So then we see the real work of that. And when we have the localization refined, we can extract the plane of the cat with the different points of the trajectory, and then execute the real cut. So here we will have to cover the camera if we are doing a real cut. And then we have also a graphical user interface to ease the process to the operators of the industry that may not be quite familiar with launching terminals and things like that. So it has a button to change all the parameters that are required, like the position of the cycle to cut. And then they also have a button to launch all the programs. So this process will be quite easy for them. And they can select if they want to localize or not, and then they have different buttons to quite the process. And here we can see the first part of the deployment of the technology. So the operators are moving the robot with the magnet, and they are attaching it to the wall and moving the rest of the equipment, like the welding machine, the robot controller, and everything. And here we see the technology working. And now the robot, you can see it's moving the tool to do the reconstruction. And now it will appear the obtained point cloud, the scenario, that the user now has to give the system the initial position. So here it is interacting with the window to tell more or less the position of the camera. You see the estimation that this process is doing. That more or less the camera. And now it will start the refinement process. As you can see, it minimizes a lot the distance. So finally, it matches the views of the reconstruction and the cut. And with that, we have refined the first initial position. This would be the position of the cut, and now the robot can perform the cut. And with that, that's everything from my side. I don't know if there are some questions or. Yeah.
There is no question.
Okay, so with that, now it's the turn of Rebecca.
Uh, I'm going to just give a bit of recap what we did. Just for you to just refresh because we have been quite long. I'm sorry that we are a bit delayed. The main important part that which we learned today is what collaborative robots are, what are the main challenges they are facing. We see embodied robotics, the challenges as well. Then we went into the safety aspects, the main challenge which we face in robotics today. And then first we see the safety devices, then we see the SSM, and then with hand guiding, followed by the application which use PFL, is basically the collaborative robot. Before ending, I just like to give you the final take-home message that the technology which we see have what we see today have basically 4 or 5 different aspects to consider. The number one is the impact that this technology has shown the benefit, but still need drastic improvement. We are working on the research side. We are improving this. We are working on different ERL levels. And we observe that the simple solutions normally are one of the best solutions. Then the relevance, we see that the technology is up to the mark in facilitating technological, for example, training and familiarity of use. However, the training courses and, for example, how the tutorials of the technology is very important. That's why today we are here also to help you learn about the technology. The utility of the technology that the devices are designed for one very specific task. So I spoke also a little bit that how you can use it for the use case design perspective for different tasks. So the cobot, if you are stakeholder buy, can be not only used for one application, but maybe for different applications. So it's very important to consider that part. And also on the productivity side is something important. Usability, why is that if a human is going to use these devices, the controller, for example, in case of handwriting or the other, will be transparent enough to move as the human desire. It's not that we need to provide more force. The safety is very important aspect. The cost should be reduced and the reach. For example, if you buy a robot, it should be have a long ecosystem. It's not that after 1 year you cannot able to find the manufacturer. So something like these are the important insights. So I just like to conclude my presentation. If you have any questions, please feel free to ask. Here we have some more training courses from different technology providers. So if you are interested, please register yourself. Here is a small quiz of 14 questions. If you like to participate into this quiz, please go ahead. It will help you how much you learn during this course. And here is a feedback form. I think that the QR code is big. It's not visible that much, but what I could do is that I just try to give you a little better. Now you can see it. So here is a feedback. This is a quiz, and this is basically the technology training which we can do. So with this, if you have any question, please tell us.